All right, so welcome everyone for Cloud Computing and Big Data. The topic of today's lecture is Lecture 4, Virtualization and Data Center Design. And this would be just a lecture we would normally had directly in line after Lecture 1, where we start with the idea of what is actually data center design, what is cloud computing, how virtualization fuels within. But as you see and noticed, we changed the ordering of the lectures basically on very much experience with students in the past. So this was mostly related to assignment 1, that this should be not coming out too late. It's also about starting with really practical topics. We have started with a real machine learning algorithm, using it in a real computing cloud, which was MS Azure. Just to pick one, we could have also used Amazon WS, web services, or even Google. Doesn't matter, but the key idea was to really start with practical subjects in the beginning so that you get motivated in the course and so forth. But now we learned a lot, and actually what we try to do now is to formalize a bit more as a university course, really, what are all the ingredients of cloud computing, and we will also notice today what virtualization really is key in the heart of the central designs of cloud computing offerings today. But before we enter the material of this lecture, let us just review what we learned before. And this was essentially the practical idea how we can perform machine learning. It's a very full slide, but it really pulls together what we learned in lecture 2, what we learned in lecture 3, what we applied then in the practical lecture 3.1. It brings all the different pieces together and is a blueprint for you to go off now and use other machine learning algorithms which are very similar. At least the cooking recipe, if you want, or basically this blueprint that you see here in the middle, is really the way how you typically do machine learning, independent of which learning algorithm you usually use or what concrete models you use from the hypothesis set. So of course, let me just make a note that this is of course a supervised learning scenario. So there are different scenarios in the non-supervised world. Hence you see training samples here have a label with it. And when we recap this, we actually started there with the training examples. We noticed in our famous, by now, food inspection scenario that we have some violations. We have the results of the food inspection of being either pass or fail. We have modeled a little bit the data and did some feature engineering of saying, okay, in the end, this is a vector that we need, so we massaged the data, as you would say in practice, and we inspected the data and have seen, okay, it's actually not 2 classes, it's 5. So we have to do more on really bringing it to a so-called binary classification problem we want. And this was largely of saying it's pass or fail, based on the violation of text. So this is how you start. You look at the data, the training examples you really have. We also said there's an ideal function that at some point in time maybe created the data. And in fact, we should say based on machine learning, we have to model it as a probability distribution, because often we have the case that the same X in gives different Y's out. And this would be not a deterministic function, as you know. It would be actually not a function. That's why we add plus noise here to the rescue. And of course, this is rooted more in statistical learning theory, things I will not cover completely in the course. And as I said, if you want to know more in this regard, please go to a proper machine learning course. Also, we said there would be some probability distribution that gave rise to the data. And which exact probability distribution that is, we need not to know. It's just important that you don't mix up things like from one streaming server, then the same probability distribution would be probably don't hold for Netflix or any other. So this is something where the data should be, of course, somehow generated from the same probability distribution. You cannot suddenly, from our flower examples, have anything taken away for our food inspection scenario. In a way that goes without saying, that's why it's more a formalization. Important in our supervised setup here, of course, are the labels Y that give you already the class information, supervised input that we can use for basically getting the training examples that we have and cutting them into training set and test set. So we would have 2 different sets. And if you Basically, continuous machine learning, you will see we also create validation sets and so on, and multiple of them if you swim in data. But these have different purposes. You train the model, you create the model with a training set, and then you evaluate on the test set if you're really good with this. So in the start this project usually in machine learning, looking at the data, then pulling away training sets and test sets, and throw the test set in the corner, don't touch it until you're really sure you have a good model you want to evaluate on. Then we said the next ingredient in this to really think about further steps in machine learning is to pick a hypothesis. And you would say, okay, it's one of the models that we have really in our skill set. We know about neural networks, we know about support vector machines. We pick logistic regression. It's really good for binary classification. If you remember, it was essentially just a linear model. Basically, the inputs are just multiplied by weight, summed up linearly with these weights, and then put through the sigmoid function. So everything, let's say, a bit simplistic, but it brings you a signal which goes then between 0 and 1, and then essentially gives you a class or the other. So with this, there are usually two elements you have to pick. And one is, of course, then the learning algorithms. Once you pick this model, a learning algorithm goes with it usually. And you would say if you have support vector machines, you go for quadratic programming. If you have artificial neural networks, you have the learning algorithm backpropagation. So they're all kind of basically together, but they are separate entities. And the one that we picked here in this idea of logistic regression was really then an optimization mechanism called gradient descent. There are varieties of them, also stochastic gradient descent, which really then tries to knock down a so-called error function and goes, let's say, with the lowest possibility on this with the gradient descent technique and basically minimizes this error. Now, the error measure is then something what you have to pick as well. And of course, with the logistic function that we have here in logistic regression, often used is the loss function, just the logistic loss, which then brings into perspective another part of our diagram, because you need this error measure to really know if you're getting better in learning, right? We want to knock down the error, we want to improve, we want to minimize it. So with this technique, you do this iteratively again and again through the training samples. You go again, you actually change the weights depending on the loss. And when you do this iteratively and be patient, and usually you converge in some point in time where the, let's say, area under the ROC curve should be, let's say, going up, or the accuracy should going up. And with this, you have a trained model. Of course, there are lots of traps in this. There are regularization entities that maybe prevent that you get stuck in a local minima, because nobody said that it would be always so beautiful with a global minima that you see there on the bottom in the graphics. And there are lots of other traps, but let's keep it simple for you firstly here to understand. And as I said, there are lots of different optimization algorithms. One key message to take away is that many of the machine learning algorithms and models you have will be fueled by optimization techniques. And with this, it's a very important topic that we have. So in a sense, over iteration, you will come to this final hypothesis that then you can test with the same x's from the same probability distribution you get without the label y. And what you should get is basically a y that approximates the real world outside very much. So in our case, of course, a pass and fail, depending on the violations in the, that you have seen in the text. And the hypothesis would be almost like the kind of target function that we approximate. So G would be very close to it. Now, you may think now, what exactly is this G, right? So what hopefully approximates F very well. So this is the logistic regression model, and that's where pipelines came into the game. You remember we used Spark for this, which is quite nice, and we will come back to this a little bit every now and then, looking under the hood of Spark again from a data center perspective and its scalability. But of course, what we did was we executing on the cluster, and it was very nice. We used Jupyter notebooks for it. We had this interesting notion of a pipeline, and this was attributed to the fact that, of course, if you train a model, you have seen we need something, a mathematical representation, which was really hard to get just from text. So text essentially needs to be transformed to something we can really work with. We call that feature vectors. So we took the raw text of the violations, we tokenized this into words, did some interesting hashing function, and then had a feature vector that we can actually use to train on. We use a logistic regression algorithm that's by now known, and what's really coming out of this training process based on the training data is the logistic regression model here in blue, right? So, and all these steps is a pipeline. That's important to know. So, and this is the benefit of this pipelines. You essentially, what we there store as a model is not only the logistic regression model in itself, which would be the G in our diagram, it is also a way of transforming the data towards a model. And this is now more popular use these days. In former times, people just have dropped the model and you then have to do all the kind of wording and the tokenizing and everything again. Instead, what we have here is that we then use it basically in the second step, which is then, just using logistic regression. And of course, if you differently times train, you get slightly differences in the model, but basically they are very similar to each other. There are differences in the model because optimization is never 100% equal. Based on these optimization algorithms, based what we have in stochastic gradient descent, it's a stochastic model, for instance. That's why 2 times training this model would be never equal. Exactly, but let's say it would be very close to it. So we would have a logistic regression model that we can use with new violations. And you see here, basically we don't need to train anymore. We just put it in this pipeline. It goes through all the process. And with this, having a logistic regression model used for some predictions, if it's passed or failed. And this is very beautiful and basically very powerful. And the way how we just dealt with all of this is essentially how you can do all supervised learning algorithms. You pick a deep learning algorithm, it will work very similar to this approach that we have here. Of course, admittedly leaving important aspects out like regularization and validation. That's what distinguishes the experts from the beginners. But of course, it's the beginning, of machine learning for you here. So that's the first steps. Now, if you go to some machine learning, you would see what are the regularization entities I have in this logistic regression. And we see there are already some parameters in our Jupyter. So there's the possibility also to regularize. But this is more an advanced machine learning topic, and I will not cover today. Let us today just now come back to, let's say, more theoretical and conceptual topics again. Inject this a little bit to get a notion of, okay, now we did lots of machine learning, lots of Spark, how that reflects now the cloud business and why is it working so well. We will look a little bit for this in a topic called virtualization, and I'm aware in operating systems this is taught to a much more detail. Here we will of course draw an emphasis of how it enables cloud computing technologies. Of course we go into some examples, we will clarify terminologies like virtual appliances, virtual machine images, instances and so forth, but we will make really a key view on this resource sharing aspect, also in the light, of course, multiple users, not only virtualization in terms of a laptop sense, we want to come to data centers. And for this, of course, it's important to think about virtualized servers, if not to a much bigger scale than these data centers. So in the second part of the lecture, then we will pick that up, the kind of key technology virtualization, and see how it really can, fuel the economics of scale approach. And we will contrast this with the total cost of ownership in the second part of lecture. So what happens if you buy all the servers instead of renting it? So there are lots of elements, though, that makes it not so easy. Otherwise, everybody would have maybe a cloud data center in the garden, right? You will see there are lots of construction features which are relatively plain. I'm talking about real building aspects of it, a second floor, diesel generators, things like that. But then, of course, also that we have real hardware to deal with. And if you have economics of scale, meaning lots of different servers, it means that system failures are there all the time. So you can imagine that large Google data centers or Facebook centers have every minute some failure in the system because they're just so large. And hardware is unreliability programmed in by heart, right? So there are always errors in the system, never 99%. So we have to prepare for this. And there are different aspects how this, let's say, data center infrastructure then deals with it. And one of the techniques really using there is, of course, virtualization, while, of course, different aspects are also related to how you interconnect the different servers, so networking aspects with it, with fat tree topologies and so forth. Then another aspect of the second part will be, of course, what data centers are very keen in and saying, we have metrics of providing 99.9 uptime. We have, provide very good scalability to users. What means scalability? We talked about it in the idea of Apache Spark, of having more worker nodes, more work can be done, but maybe there are different scalability requirements also for users that we didn't previously touched on. And then there's a very important notion that we close with today, which is really then the idea of public, private, and hybrid cloud deployment models. So this is something which is a way how you operate clouds, and we will talk about it. And it's very important to differentiate those also from the infrastructure as a service, platform as a service, and software as a service layers that we will have in the next, in one of the subsequent lectures. So we will talk about this, and with this we also fulfill some of the promises we had in lecture 1. As I said, lecture 4 in a way would be the consecutive one after lecture 1, but we inserted, so to speak, based on student feedback, really this practical lectures to be, a more interesting course. So let's start a little bit with virtualization, and I think some of you know that topic very well, so we can go through this, I think, in a more advanced pace. Many of you probably also taking the course operating systems where you learn a lot about these things. So just think about that, the history that this got, that we had already in lecture 1 was really different networks, different ideas of so-called computational data grids led to these internet clouds, and the way how we used in grid computing when we worked with CERN 15 years ago, virtualization was just starting, right? Of course, the systems and the ideas date back to the 60s, but the real, let's say, rollout of virtualization in broad fashion just came out the last 15 years. So, of course, it was an improved pace. And this was really fueling the internet clouds directly, but also indirectly other technologies, which are Web 2.0 services, Internet of Things, we not really focus in this cloud on, in this cloud course on, but of course are very relevant topics also outside. And you can really state that cloud computing as a paradigm as it exists today would be not possible without having the virtualization technology. That's really a key important ingredient in cloud computing today, and we will make a case for it. So when we think about the virtualization concept, as I said, the ideas of this have been quite a long time existing. And the general idea is that why should be just one, using the hard disk? Why should be just one guy always using the computer, the hardware, the CPU, the memory, everything you have in hardware at one point in time, and then, leaves the office and the system is not, used by anyone. So you see there on the top right, why not enable more people to go and use the hardware in a way? Of course, this is not that simple, right? So you need some software layer. So you need something that is really managing this. If you have just a bunch of people using storage, as you see on the top right, it would be probably looking more like a kind of crash scenario or a helper scenario with a natural disaster. So this means there's some really need to use a hardware from, let's say, more than one, but also really to steer that with some software technology. And of course, if you know a little bit about hardware, this is also not that easy because we need the hardware for storing files, for getting computing done. So there's an enormous interaction that takes place between the operating system or the software, the application you have, and the hardware all the time. So it needs to be an entity which is quite powerful that sits in between. And if you look on the bottom right, you see essentially the difference between a traditional computer where you say you have a hardware, you have a so-called host operating system. And within this host operating system, that could be a Linux, could be a Windows machine, even a Mac, there's some form of application that, exclusively, so to speak, uses the hardware through the host operating system. Now, what virtualization does is it inserts a layer on top of this hardware, right? And this is an interesting aspect because now I'm having so-called emulated devices. So the hardware is not really existing, it's more virtual. And on top of this, I put a so-called guest operating system, which is different from the operating or host operating system I have installed, but could be, enabling lots of possibilities, like, for instance, having maybe a host operating system in Windows, but having a guest OS in terms of Linux on top of it. And this is, of course, an interesting model. So the virtual machines, in a way, enable us to really abstract and making more possibilities for different applications to be use of hardware, and on top of it, really to have much better system efficiency, because also, of course, we thinking about this about a multi-user setup. So these virtual machines can be used not by one user in different flavors, so one virtual machine or another. Of course, we can think about a data center design where lots of people use different virtual machines, independent, so to speak, directly from the hardware, and with this do resource sharing in order of magnitude. There are lots of terminologies now which are new for you, so I will go quickly through them before we really think about the data setup or the data center setup. So the virtual machines, again, if you look on it on the bottom right, is a little bit clear. We have hardware where there's this operating system, the host in the left side, and there's some application. Now, the idea really of the native VM would be that you have some form of a hypervisor on top of it. Virtual machine manager would be another idea of how to call it, but it would be responsible for managing all of this virtualization. And of course, if the guest OS, which is used to sit on the normal hardware usually, just want to have a call to the hardware, there needs to be, an interaction between the hypervisor or the VMM in order to do what basically the hardware should do, like reading from files or basically access a CPU for some computing. So essentially, you have a non-privileged space in this, which means you need the VMM to be a little bit in a privileged mode to do really system features, to have really access to the hardware. And of course, if you think again, this should be maybe multi-user, it should also think about much more the different user privileges. So here, the native VM stands for bare hardware, right? And we will come to different notions later, how that is different from other terminologies. The virtualization layer is thus very important. It is basically inserted by this virtual machine manager, and it really creates an abstraction for the virtual machines. And this could be on different layers, as we'll see later on with a couple of examples of hypervisors and so on. So there are interesting models that it's not only that plain as you see now, there could be different ways how you install that. But interestingly enough, again, we have, let's say, different operating systems that can work on top of this, making it a real nice feature. The virtual machine manager itself can provide full virtualization. So that means it's basically almost identical to run on the typical physical machine. And with this, it's already interesting if you run, different virtual machines on this, you really can enhance the utilization of servers by it. Of course, the VMs needs to be isolated, which means secure from the data from perhaps another user or from another application. So this is, of course, something which is important. But the interesting thing is you want to really think about it as a system in its own. So in a way, you would say the applications, the operating system that we have as guests could be, let's say, as a fully virtualized solution running everywhere where there's such a hypervisor. And with this, I have also interesting things of saying it's completely independent from the hardware. I just have to do, compliance with the VMM on the hypervisor. So this has taken lots of, interesting uptake then in the cloud community and large server designs where you have multiple operations you can work with. So one of them is, of course, multiplex VMs we already seen. So when you have one type of hardware, you can have different VMs on top of the VMM manager. and sharing the hardware, because in the end it's virtualized. So the VMM will make sure that there's no, let's say, problems if two users at the same time use the same hardware. Will basically through the guest operating system manage this multiplexing of the VMs. Then, of course, we have the idea of suspension, which is very attractive. If you think about that, this is anyway all virtual. Nothing prevents us of saying it's just bits and bytes. Why not putting it to storage? So this enabled, so to speak, to have a real idea quickly drop to disk in terms of the whole setup of an operating system, of applications with it. And this is quite interesting and very incredibly used today also in terms of images and so forth and instances that are saved. I come to that in a moment. And of course, once you have dropped it to disk in the suspension mode, so to speak, you also can resume it at some point in time. And this is, of course, another idea also why resource utilization is so interesting with this. You suspend it if it's not used, and if it's used again, you provision it again, and then using cycles again. So, and in the meantime, other users can maybe use the hardware because the other ones were suspended and not used, still having the same state if you basically bring it back to life. And then what really is a key element today, I will bring you an example for clouds, is live migration. So this is something where you can think about in former times completely unthinkable, that in a couple of milliseconds now, complete applications with the operating system, so to speak, can hop to a different hardware. And actually this is often true because of failures, right? So as I said, the hardware of large data centers fails again and again. It's just normal, and different reasons for it. But the application operating systems are smart enough today to have early indicators of that and could actually pre-staged already to a different hardware, and with this surviving the whole world crash. Let's say if we see the heat goes up significantly, which means probably somehow this system is damaged or broken. This is an indicator to do perhaps a pre-migration, and then basically are very quickly able, when the system really breaks, to jump over. And I brought you this example here, which is essentially the same thing that I said, that you monitor it on the bottom right. You see there's something with concurrent clients, everything works well, and suddenly the throughput of this web server maybe that you operate is dropping. So this is the first indicator where smart systems today start the first pre-copy of some of the states for further iterations. Of course, it will be still monitored, and of course this transfer should be not something which should take a lot of footprint, right, in the transfer. So it will take some time to really iterate or to basically transfer all this to another host system. And then you see suddenly at some point in time when the machine really goes more down, we see the throughput of the server there's something happening, then we migrate. And you see here as an example, that meant just for the service and the application a 165 millisecond total downtime. In other words, the user will never notice. Right? So this is a very key ingredient of these VMs today. I put the whole state, everything with live migration very quickly to another server. And usually that works very well, so that this is, let's say, not even an interrupt for users noticing, especially if I have a good monitoring system looking on the state of the systems. This is today, I guess, of course, almost everywhere in the commercial space, and also quite broadly applied in the academic sectors running clouds. Coming to some consideration how it looks now when you think about commercial clouds, you would think like they offer you virtual machines. And for some of you that played around with Microsoft Azure, for instance, you will notice it's not only good for creating Spark clusters, you can do a hell of a lot of other things. And a good way of, how they deal with it is virtual machines. They have a very nice way of creating different virtual machines from so-called images, which means you have already a pre-setup, you see that on the right-hand side, of selected operating systems from an Ubuntu server, from over Debian, Oracle, up to Windows servers even, that you can choose from and create. You combine it with your subscription. Of course, it costs, right? We have discussed it already. Everything in the cloud costs, and there you will find also money values, or basically the cost explicitly explained for the virtualization. So when you have this appliance then, so in a sense you have the operating system, and you could even have something on top, let's say Windows Server, which is for data centers 2019 here, for instance, on the example on the right. So then you talk about a virtual appliance, right? You have really the resources there together with some installation of an application. And with this is something where you don't have to install anything. It just comes automatically once you buy the service or you host the service in your cloud, you deploy it, and then you can use it. Of course, you have to configure some SSH keys in order to access it and do something with it. It's not that automatically Jupyter is on board, but it's another idea of appliances. So you would have the Spark example where we had Jupyter notebooks already installed, everything, that we don't even have to think about any installation of Spark or Jupyter. It's just the same way, just a much more powerful virtual appliance than just the operating system. And this is, of course, now a model where all the cloud vendors work on. And with, you have seen live migration, all of this comes really alive of being, let's say, interesting to maintain, because of course now you can automate a lot of processes. You have seen the templates for creating essentially a whole Spark server. You have templates for creating virtual machines with their corresponding images. So let us review a little bit what compared to the bundle we just discussed is now the idea of an instance on an image. It's pretty clear essentially when you say that virtual machine instances are real life. They have, let's say, really a running time now on the server. And an image is something what you see here again on the right-hand side. When you create a Microsoft Azure virtual machine, you can choose from. This is something which is in storage essentially, that will be then, for you either downloaded in clouds. You can select them and you create an instance from these images. And of course, this would be something which is then managed by this virtual machine managers. And it's of course very dynamic, so existing from different catalogs, they are changed over time and so forth. But the beautiful aspect of it is already maintained, it is configured with good security setups, with operating system updates regularly. So all of this you also don't care about, you just essentially buy it directly from the cloud. This brings us to different software architectures towards the end of the first lecture, because of course, can think about that this virtualization layers we discussed, the idea how to use virtualization could be different. And also from the perspective what you allow a virtualization entity to do, because it's still very powerful. It can essentially take over the whole system when the hardware is underneath. And with this, you want to see how you essentially grant different rights between the host and the guest OSs on different architectures. And we just running through a couple of them. They are not, let's say, majorly important right now for your cloud computing course. It's just a more form of for completeness actually mentioned here. So the first one is an example of Zen. I think some of you heard about it. It's more a hypervisor architecture, which also shows you that I talked about the guest operating systems being always equal. Here we have an example in Zen that the domain 0, as it is called, essentially is a very special operating system, which is more or less operating like the host. So there are different guests basically that are there in the domain U, which could be a Linux system, a Windows system, but the domain 0 is a very special one. So it's not any more equal. And with this, the applications running in domain 0 and of course in the different domain U, Windows and Linux, have different rights, what to do and what not. So this is something what is basically to consider if you have, for instance, the hypervisor architecture with Zen, for an example. VMware operates oft workstations with full virtualization. You see this on the bottom right, where you have, again, of course, the hardware is always there. They have the VMM, the virtualization manager. And basically every time when the guest operating system really wants to access the hardware, so-called traps are activated, which are critical instructions where, basically this is something where the VMM has to emulate something from the hardware. To also guarantee that not other users at the same time access the hardware. They have to have a mechanisms, for locking and so forth. In all, this whole emulation process is a form of binary translation, but it's really as far as you need to know. because of course there are lots of non-critical instructions also that the operating system does, or basically even a direct user from his application can do in some form using APIs of the guest operating system. So with this is just a different model, this full virtualization. You have host-based virtualization architecture, which is very similar like the first one we've seen. There's again one host OS and basically also a guest operating system. An example is that you operate Windows usually, but you have also Linux guest operating system that is often used, for instance, in academic setups, to use LaTeX, to use different from Linux, but still have the power of, you know, PowerPoint and so on in the Windows area. It's also very often used. Then there's a Para-Virtualization methods, which is interesting because a guest operating system has some, let's say, very interesting hypercalls, so to speak, non-virtualizable instructions, which are specifically designed for these. Of course, this means you have to always have updates on your kernels on this, which means brings you also to the name kernel virtual machine. And this means also the maintenance is relatively high of these solutions. But KVM, for instance, is a part of the Linux operating system, so also used. And of course, interesting that for us here, the hardware environment is not really simulated like in other approaches, for instance. But let us look forward to the second part of the lecture when we think about cloud computing. What is it? We said data centers are fueled by virtualized resources. We will see here in the second part of the lecture much more that still the physical hardware is there. We have a virtualized platform, which means they are already virtualized in the sense of being all together accessible. And then you would have different virtualized infrastructures on it, where you have different solutions running in a virtual machine, sometimes bigger, sometimes smaller. You need lots of infrastructure services with it, load management, virtualization services with it. And of course, all of this topic is so broad, I cannot talk in this lecture about it. We have a specific lecture 13 that will talk about cloud operating systems and really will also pick on the important part of security, which we actually leave in this lecture and pick up on lecture 13 much more intensively. In a way, this is all about data centers, about resource sharing, but then also about disaster recovery. Think about and be stimulated by the fact that Apache Spark can be used by different users, not only one. We have this yarn scheduler, and it looks like from a Jupyter notebook, you're the single user, but in the back, there are many different users using it. So it needs to be sharing the resources over the internet, over the different LANs, ZANs, and so forth with each other. And then we have seen the live migration of VMs. Of course, this should be, let's say, with a relatively low overhead, as we've seen, if there's an error happening. And you don't want to know that when you do Spark, right? You don't care, you just want to have your machine learning algorithm done. So in the end, we will talk about physical and virtual processors in that way, where you see on the right-hand side, you have virtual CPUs you can often buy in the cloud, but in real underneath are physical cores, but you don't really see them. You buy virtual CPUs. For the I/O devices, they're usually emulated, basically, and emulates just the virtual device because you share it with many others. The same is true for large many-core installations we see today, with lots of GPUs interconnect. So there also VMs need to be, of course, very much mapped into adjacent cores in order to have a good performance using NVLink, things like that, which are important for GPU clusters. We will elaborate on this also in the deep learning lecture a little bit more. So all of these are interesting topics and basically just examples here. This is a VMware ESX server. That is an example how you can have a commercial solution for it. But as I said, all this topic is very intense in terms of how you, from the software perspective, create a cloud. And we will revisit this in lecture 13 much more in depth. So this is really all I wanted to say today for this first part on virtualization. Here's a very good video, in my opinion, that you should look at if you want to have a summary of all we just discussed and talk a little bit about standardization. And this is, of course, also an important part.